Welcome everybody. Today we are going to build a churn prediction model. This means that we are going to build two workflows, one to train the model and one to deploy the model and use it on real life data. Churn prediction is a very common task in data analytics and basically consists in trying to predict those customers that are going to quit the contract before they actually do that. This is for obvious reasons because, of course, if you find out which customers are going to cancel the contract, you can intervene and somehow convince them to actually renew the contract, keep the contract, and not cancel it. So it's a very common process. We need the data of the customer. Usually the data of the customer include contract data, demographic data, operational data. For example, in this case, we are going to work on telco data. So we have available how the customers have been using their cellular phones and their telephone plan. Okay, so let's start with the training. I have prepared this workflow, churn prediction training start empty. It's an empty canvas for an empty workflow. And the only thing that I have available here are the steps that I'm going to include in my training workflow. Okay, so the first thing to start from is the reading the data, of course. The data has been placed in this folder here in my KNIME Explorer. And you can see here I have a calls data file, which includes the operational data of the telco customer. So how many minutes he spent on the phone in the evening, how many minutes he spent on the phone during the day, how much he paid, and all this kind of information. And then I have the contract data for the same customer. The contract data means some demographic about the customer and mainly the kind of plan costs that he has signed up for. One is an Excel file and one is a CSV file. So let's then read the first data, the contract data. Just drag and drop the file into the workflow editor of KNIME. As you see, when you drag and drop a file into the workflow editor of KNIME, KNIME automatically creates the correct reader node for that particular file. In this case, we are dealing with a CSV file, which means we have to create a file reader. So a file reader has been created. This is the path for the file that we want to access, and this is the preview of the file. In this case, we see that the structure of the file seems to be correctly interpreted by the file reader. Here there are a few more options we might want to access if something is wrong in the preview of the file. Here there is the advanced button if we want to access some special settings for the file reader. But here it seems it was an easy file. It seems the file was easily read, so no problem. The structure seems to be correct, so let's click OK and let's move on. So let's put a comment in here and let's write reading contract data. Okay, now same thing we do with the operational data. Let's drag and drop the calls data file. This time is an Excel file, so it automatically creates an Excel reader node. So let's open the configuration window of the Excel reader node and let's see if the Excel reader node has been as marked as the file reader node and guess correctly the structure of this file as well. So here you see there is the path of the file, so that's correct. Here you see there are a number of default options and they seem to fit our purpose as well. And here you see there is the preview of the file content, but something here is wrong. In this case, it didn't read correctly that this first row is actually the column headers of the file. So let's say table contains column names in row number 1, and then let's press refresh. Let's click refresh to refresh the preview of the file. Now the structure in the file preview looks correct, and we can say OK, and then we can write a little comment under the node. So for example, reading operational data. Good. Let's execute these two nodes. So let's inspect the content of the two output data tables of the two reader nodes. So in this case, we are going to have the contract data that contains some account information, contains the voicemail plan, the international plan that the customer has, and a telephone number and an area code number that identify my customer. Also, it contains a churn column indicating whether my customer has renewed the contract or has quit the contract. 0 has renewed the contract, 1 has churned, that means he has quit the contract. Okay. Now let's check the content of the second file, and here we are going to see more operational data. So we are going to see, for example, how many voicemail messages have been recorded, how many minutes have been used in the evening, how many minutes have been used at nights, and how many minutes have been used for international calls, and so on. And again, every row is identified through an area code and a phone number. So those are my customer ID, the area code and the phone number. We want to put together the information coming from the contract data and the information coming from the operational data. To do that, of course, we need to use a joiner. So let's use now a joiner node here. Let's connect the contract data to the joiner node, and let's connect the operational data to the joiner node. Let's open the configuration window of the joiner node. So I join on the area code and the phone numbers using the area code and the phone numbers as my unique keys to identify each row in my data tables. If I move into the column selection tab, I have the option of either include all the columns or select some of the columns, but I decide to include all of the columns. This option is going to filter the right joining columns, so I'm going to retain only the area code and the phone number only once in my output data table. Okay, so let's run it, execute. And then let's inspect the results. And even here, we are going to see the data from the first data table. So all the churn and the account information and and then we have all the operational data, the charge per day, the number of calls per day, and so on for the same customer. Okay, that means for the same telephone number. So if we check the join table, we are going to see that the churn has been read as an integer. We are going to use a decision tree because a decision tree produces a tree which is easy to interpret. We could use any other model for our churn prediction model, but the decision tree is the easiest for demonstrational purposes. Decision trees require nominal values as classes. Churn has to be expressed as a nominal value. So to do that, to change from integer to nominal values, we are going to use a number to string node. Okay, let's connect it again, the number to string node. Okay, and then we are going to remove all, and we want to convert just the churn into a string column. Okay, so execute. Let's see, let's inspect the output, and now the churn has the same values, but they are strings and not integers. So let's write here some comments, converting churn from int to string. Good. Okay. At this point, we want to color the rows using a color scheme. That's always good. So why not? So let's use the color. We go into the data views, properties, and we take this color manager. The color manager assigns colors to each data row of the input data table. So open the configuration window. We want to color not by state, but we want to color by churn. Oops. We want to color by churn. Blue, the people who have not churned. Red, the people who have churned. So let's execute again. Let's open the output table, and we can see that when the churn is 1, there is associated a color red. Otherwise, the color associated with each data row is blue. Now we need to prepare to train our model. Usually, the model training has two phases. The first phase is to train the model, and the second phase is to evaluate the model that we have been trained. That's important because if we don't evaluate the model, we might end up building a model that doesn't perform very well and therefore is useless. To give space to both phases, training and testing, we need to reserve some data for training and reserve some data for testing. To do that, we use the partitioning node. Partitioning node, that's the one. Okay, so let's connect the partitioning node to our color manager. Okay, Hopla. Okay, so now let's suppose we want to use 80% of the data as for training set and 20% of the data for testing. So we use the relative partition, so using percentages of the data. We produce 80% of the data on the top output port, and let's say we draw them randomly. We can also use a stratified sampling using the churn for the stratification. Stratified sampling means that we are going to produce an 80% of the data, a data table containing 80% of the data, where this 80% of the data was extracted from the original data following the a priori distribution of the classes in the churn column, in the selected column. Let's use, for example, the stratified sampling. Okay, so again, execute. Now at this point, we are going to have two output ports, two output data tables. The first data table at the top port contains 80% of the original data, and it's going to be used for training. The second output port contains 20% of the original data, and it's going to be used for testing. So let's continue then with the model building, and let's go on with the training. We are going to use a decision tree, we said. So the decision tree learner is the node that I'm going to use to build my model. Okay, so let's connect the training set to the decision tree learner, and let's configure the decision tree learner. The class to be learned is churn. The quality measure can be the Gini index or the gain ratio. Okay, we can apply pruning or no pruning. Let's say we want to have a minimum number of records per node as 6. The higher is this number, the shallower is the tree. The smaller is this number, the more detailed is the tree. So this is an important parameter to keep in mind to define how detailed the tree is going to be. We are going to use the average split point. We are going to, skip the nominal columns, and we are going to use, for example, binary nominal splits. So if we have string columns with many possible values, I'm just going to have a binary split of those possible nominal values rather than a split with all possible nominal values. So this one makes the tree a bit more compact and maybe more general. We click OK, then we execute the decision tree. It learns, and as we can see, the output is a PMML model, so it's not something that we can visualize easily. The blue square is a PMML model. The white triangle is a data table. We can see the output of the decision tree learner, which is a model, but it's not easy to interpret. What we can interpret it much better by using the view of the decision tree. So let's open the view of the decision tree, and here it is. You can see that the first cut is a day charge. If more than 45 dollars are spent on per day, the probability that the customer is going to churn becomes much higher. If there are even less than 7 voicemail messages per day, then the probability that the customer is going to churn becomes even higher, and so on. So we can really follow the decisions produced by the decision tree. So if the charge for evening calls is higher than $13, so that means if the plan that the customer is using makes him pay more than $45 per day and more than $13 per evening, basically it's too expensive, the likelihood that the customer is going to churn is very, very high, especially if he lives in one of these states that are represented here. Okay, so now we have our decision tree learner. We said we want to evaluate. The decision tree learner is the node that builds the model. The decision tree predictor is the node that takes the model and applies it to new data. We use the model produced by the decision tree learner to feed the decision tree predictor, and we use the test data set that we have created with the partitioning node to feed the decision tree predictor as well. The decision tree predictor doesn't have much of a configuration window since all the information is already included in the decision tree model. However, there are a few tuning that you can make about the naming of the output columns and about the appending the columns with normalized class distribution. So let's just enable this appending the columns with normalized class distribution flag. Okay, let's run it, execute. And now we can inspect the output data, and the output data is exactly the same as the input data, besides these last three columns. The first column is the probability that the customer is not going to churn, so the probability that churn is equal 0. The second column is the probability that the churn is equal 1, so the probability that the customer is going to churn. And the last column is the decision that the decision tree has made based on these two probabilities here. So when one probability is higher than the other, that's what the decision of the decision tree is going to be. Okay, so how are these decisions? Are they correct? Are they wrong? Is the decision tree correct most of the time? Only a few times? How good is our decision tree model? So let's see how many times it was right, how many times it was not correct. To do that, we are going to use a scorer node, a simple scorer node. The scorer node does exactly that, matches the original columns with the original class values with the predicted columns with the predicted class values. Okay, so we want to compare the values in churn with the values predicted by our decision tree. Let's run it, execute, and now we are going to see that there is a confusion matrix. This diagonal of the confusion matrix contains the error. This diagonal of the confusion matrix contains the correct answers, the number of correct answers. If we check the second output or the data table at the second output port of the scorer node, we can see a number of accuracy measures. So usually we refer to this accuracy measure, and we have a 93% of correct answers. Let's now save the model that we have created with the decision tree. The model is PMML formatted, so we are going to use a PMML writer node. So PMML writer. We connect it to the model. We then input the path of the file. Okay. We give override permission because in this case it already exists, and then we execute it, and then the model has been saved. Once the model has been created, we need to apply it to real-life data. So let's suppose that a customer calls the call center, then the agent of the call center retrieves the data of the customer, feeds the data into the model, and evaluates the likelihood that this customer has to churn. Depending on how high this likelihood of churning is, the script that the call center agent is going to follow will be different. To feed the model with the real-life data, we are going to use a different workflow, which is called a deployment workflow. A deployment workflow is a workflow that applies a model to real-life data. Okay, so the first thing to do then is to retrieve, in this case, our new data, so the customer that calls into the call center. Okay, so in this case, we just drag and drop like we have done before. So we see here, we change the read row ID. Okay, we then run the file reader, and then we evaluate the data table that has been created by the file reader node. Okay, in this new data, as you can see, there is no churn information. All the other data columns are the same, but there is no churn information, and that's what our model has to evaluate. So let's suppose that that's our model. We check the configuration window that doesn't require much, just the path of the model, and then let's run it. Okay, and here, so we have here available the data for the new customer, and we have here available the model that is going to evaluate the data for this new customer in terms of churn prediction. Okay, so now we have here a PMML reader. We know that this PMML reader is coming from a decision tree. So we can use a decision tree predictor. And we can feed the decision tree predictor like we have done for the evaluation set. We can feed it with the new data and with the model. However, this is a PMML model, we have said. A PMML model is a standard format for models, including also the kind of model that is contained in the file. So in this case, for a decision tree or for a neural network or for whatever the PMML model is containing, I can use either a PMML predictor or a JPMML classifier. Both nodes, so this is the PMML predictor or the JPMML classifier, both nodes are PMML interpreter, so they get as input the new data to classify. They get as input the model on which to apply the new data, and they correctly interpret the kind of model and the kind of predictor that they are supposed to apply for this particular model and input data. So the configuration window is very minimal. Like all the predictors, there is only the option to append columns with normalized class distribution to the output data table or to change the prediction column name. Okay, so let's run it, execute. And here we can see the results, which shows us that we have the probability of not churning for this particular customer is 0.15, very low. The probability of churning is 0.85, much higher. And the final decision taken by the JPMML classifier is the prediction is 1. So the customer is very likely to churn. If we want to pass this number, so this probability of churning, to a tiny report that I have already prepared, okay, so here we can just move into the reporting environment of KNIME, and we can see, okay, apply, and we can see that the preview of this particular report includes a little information about the customer, like, for example, the probability to churn, and a little speedometer that tells us how close to the dangerous zone of churning this customer is. In this video, we have created a model, trained the model to predict churn, evaluated on a test set, and finally applied the model in a deployment workflow to work on real life data. And everything in less than half an hour, and even with all my talking. What we have created here is a very basic model. Of course, this model can be improved by changing, for example, the machine learning algorithm that has been used to train the model, or, for example, by applying an optimization loop and optimizing the parameters of the machine learning algorithm and applying many more other tricks that are useful to improve the classification accuracy for the selected machine learning algorithm. Thank you for watching this video, and I hope it was useful for you.